course, again, even though we're potentially lowering flow rate, there's still more volume that's going downstream. We're not retaining that extra volume and saying you have to keep it. It's still being allowed to go downstream. And recently, with the updates to the unified sizing criteria, we added a little bit more guidance on even thinking about even bigger storm events. We had the events that hit West Des Moines and Clive and Johnston and Ankeny last year, where we saw anywhere from 4 to 10 inches of rain over a large area of the Des Moines metro. Just about everybody, I think, got hit to one degree or another. So it makes you think, those aren't events that we typically design for necessarily, and we're not saying you need to detain and hold that water to that level, but we are saying you need to be mindful of where it goes. When you build a basin, we want to make sure you have auxiliary spillway so you know where the water goes when the basin fills up and it spills over. And we'd like to have easements or other ways that that somebody didn't build the building in the way before it can get to a stream or something else. So just being mindful of, hey, there's always a bigger storm. We want to make sure we're trying to give that water a chance to get out. We're not saying detain it, but just make sure it's got a safe way to get out of your development or out of your stormwater practice if it happens. So this is for the 100-year, the comparisons. They aren't as stark and big as they were for the 1 year, but again, you can see that the natural level is down much lower than the post-developed peak. And the difference is not nearly as big as for the 1 year. I mean, you're talking about a peak rate change that's about 4 times, and a volume that's about a little less than 2 times. So it's not as stark a change as you see with the smaller storms, but it's still an impact. So if we're going to meet this objective, what does that mean? How much space do I need? If I'm planning a development or if I'm planning a regional basin in a watershed, what do I need? Well, you're going to have that reduction inflow to outflow. You're going to end up shooting for about 60 to 85% reduction. Again, it depends on what the conditions of your watershed are to meet that release rate goal. Typically, that ends up working out to be about 30 to 50% of the rain that falls. So that's going to be anywhere between 2.1 to 3.6 inches. So we started all the way at the bottom of the pyramid, needed to manage about an inch. To get up to this highest level, you're probably needing to manage, between 2 and 3 inches. And it just depends on how much impervious cover you have in that watershed. If it's more like a single-family residential subdivision, you're going to be down in that 2 range. If it's high-density commercial corridor, it's going to be, up over 3. When you work the math, though, and if you assume that you can get about 5 foot of depth in a detention basin, that means you dedicate anywhere from about 4 to 8% of the watershed area to achieve this goal. And this is the goal that requires the biggest area. So ultimately, where the rubber hits the road, how much space do I need? That's kind of a good target to be aware of how much space it would take to meet this. And again, this is the unified sizing criteria all together, kind of nested within. So if you're meeting this upper standard, you're probably able to meet all those other ones kind of within the same area or with some practices adjacent. So I threw a lot of information at you. I threw a lot of words up on the screen. Could this actually work on a practice? How does this function when it rains? So here's an animation that Mike Perez did, that kind of shows, water quality practice. This may be more of an infiltration practice, actually, where there's ground there, where it's soaking through the ground, but the water would come in and would slowly release over time. And then there's a next stage, you can see there, like a smaller pipe. So when we get that 1 year event, it's not just blowing out a really big pipe, it's only going to go out this smaller outlet here, and then the under drain over through here. So it's only going out through these 2 small outlets. So again, that water is going to go out a lot more slowly than if it was going out through the big pipe. In the past, how we've designed a lot of these basins was we would use a single stage outlet that was only sized for that really big event. So it might be 12, 18, 30 inches, depending on how big of the basin it is. Well, when you get a little rain event, it just runs right through that big pipe real easy. By using a multi-stage design, it has to go through these smaller stages first, which allows it to slow down that water from that 1 year storm a lot better. Then if we have the bigger storms that happen, they can get up to a higher stage that lets the water go out more rapidly. So it would go out through the sides of this inlet, and then eventually it would go out through the top of the inlet, and perhaps it might even go over an emergency spillway when you get because we don't have to restrain those bigger storms nearly as much to achieve those goals as we do these small storms. So it doesn't make the sense to make it go through that little outlet for all the storms. As it starts to go up to bigger and bigger storms, it can spill over into more parts of the outlet, and it can let more water out. But it achieves all those standards. Here's just another example of how this can be built into, it doesn't have to be a really elaborate or expensive structure. This is simply a precast area inlet. Normally maybe it would just come up and have one opening at the top. But by putting small openings in the front, like a smaller pipe that comes through the front, and then different little levels that are cut on the sides of the structure, either like a lower weir or a higher weir, we can control the flow at those multiple stages. So it could be a small little 4-inch pipe that the water goes through first. Once it gets up 2 or 3 feet up off the bottom, it then goes through this weir on the front that's a couple feet wide. Then as it goes up another couple of feet, it's going to spill over the sides of the structure and let the water out faster. And then ultimately there's an outlet pipe that at some point is going to be the thing that becomes the restriction and slows the water down. And then we always want to plan for, there's probably, in case we get another 10-inch rain event, we have an emergency spillway that water can go. So this is not a one-size-fits-all outlet, it's a multi-stage. And you can see how that could potentially work. And I have to apologize, my animation is not nearly as cool as what Mike Perez's was. But this will give you an idea of how this could work through the different storm events and the different aspects of the unified sizing criteria. If we get that channel protection event, which is a one-year event, so about 2.67 inches of rain in 24 hours, almost all that water we want it going through that small pipe. And it's going to, I had a 4-inch in this example, but it really depends on the size of the watershed. Sometimes it's going to be 6 inches, sometimes it's going to be 10 or 12 or whatever. But the goal is this smaller pipe slows that, it catches this water in the basin, and that small pipe really, really slows it down. So it has to draw down over the period of longer than a day. So that water's just going out this outlet. And we design it so that the next stage is above the high water of where we expect this storm to get. We don't really want that water in this storm to go over that next weir. When we get a bigger storm, if we get the 10-year event, it's going to fill up to the point where it gets over to that next weir, and it's going to crest over, and it's going to spill in the inlet. It's going to let that water out faster. But we're still letting it out at a more natural rate. But even the prairie would have shed a lot of water in a 10-year event, so we can let more water go out faster. Then finally, if you get that extreme event where we're talking 7 inches of rain, this is how it would operate. Now it's filled up over everything. It's spilling over the sides of the inlet, and even the outlet pipe is running pretty much full. So you can get an idea of how having the outlet structure built a little differently can help us manage both the small storm and the big storm more effectively. And I guess, what time are we at? We're doing good. I just wanted to check in. One other thing I wanted to mention before I wrap up on the unified sizing criteria is the rainfall values that I talked about and where those come from. And there's been a recent update in that NOAA has put out, which is called Atlas 14. So even up to 4 or 5 years ago, we were using design rainfall rates that were lower than what we use today, because they did an extensive study over 30 or 40 years of rainfall data and have discovered that over the last 30 or 40 years our rainfall has gone up. And it's gone up, I know in central Iowa it's gone up about 20% over the last 30 years. So we can expect some of those storms to happen more frequently than they used to. So NOAA issued new tables, new design tables for the different rainfall events and how frequently they occur in different areas. And you can go to their website and you can look up any spot in the United States, where you're at and what the rainfall rate they project to be for the different types of storm events. So you can log in to Ankeny if we were at the DMET campus in Ankeny, And you can see for the different storm durations, like different storm durations have different rainfall values. So obviously the longer the storm goes on, the more rain can happen. But some of these smaller storms, it may fall very, very intensely. But what I want to point out, mainly on this chart, is the numbers that went into the ISWIM manual are the same numbers that are in the SUDAS manual right now. And what they did for the SUDAS manual is I think they looked at the rainfall rate at every county seat in a region, and there are 9 regions across Iowa, and then they averaged those. And that's how they came up with the rainfall rate for that area. So central Iowa is based on the counties that are around Des Moines. But what I would point out to you when we talk about these design values is these numbers are not absolute. They're not perfect. Their statistical analysis here, the numbers that are the biggest numbers, they're telling you that there's a 50% chance that the rainfall design rate is actually lower than that. And there's a 50% chance that it's actually higher than that. So it's kind of the center of the road. Like in Ankeny, that I mentioned the central Iowa value we use is 7.1 inches. In Ankeny, it's 6.9. So you can see they're really close. But that's what they think the 50% number is, the average. There's a 5% chance that that number is 5.4 inches or lower. But there's also a 5% chance that it could be as high as 8.6 inches or even higher. And we've seen this upward trend in precipitation over the last 30 years, and then there are also some climate studies that suggest it could go up another 15% by 2050. Why I bring this up is I just want you to be aware when we're talking ISWIM and I'm talking all these storm events, what the designs are based on. It's that middle number. You know, you could make an argument that you may want to pick a number that's, you have more confidence that it's not going to be more than. You know, you could inflate that number and say, well, we want it somewhere between 6.9 and 8.6%, you know, so that it's only a 25% chance that it's going to be higher than that. Or you could also say, you know, we think the trend of precipitation is going to increase. We want to build that into our design. That's not what we've done with the Iowa Stormwater Management Manual. The rainfall values that are in there right now for design are based on this atlas, which is based on the rainfall rates over the last 20 or 30 years. I think we as a group felt that that was a sufficient enough factor of safety, but I'm just bringing it up so you understand, you know, these numbers aren't absolute perfect, that there is kind of a range that they could be in. They could be higher than what we project, and they could increase in the future. So there's always room for discussion on, well, should you do more than that to have a greater factor of safety? But we were trying to balance, you know, having better stormwater management practices versus like not make things more costly than they really needed to be. So it's always tough to find that right balance on where that line should be drawn. So I just want to be clear, that's really where the line is it's kind of that middle level. And these numbers are still higher than what had been used over the, you know, if you go back 5 years ago, the numbers for design would have been a little bit lower. So you can see how some of those things are graphed out. If we drew a line on that 24-hour graph, you can see all these different, you know, on average, you know, what happens about once a year on average versus what might happen once every 1,000 years on average, you know, kind of graphed out in space there. And as I mentioned, they took all that data from the different county seats and they aggregated it for 9 different zones around Iowa. So what the Iowa Stormwater Management Manual does is says, hey, for the Des Moines area, you use Section 5, which is central Iowa, which is based on the rainfall rates for right around here. So they should be, you know, if you went to that website and got the actual values for your town that you're in, they should be fairly close to these values as long as you're working in the central Iowa area. If you're working somewhere else in the state, you have to refer to the different sections in that table. So I'm about finished, but just to give you a quick recap of the unified sizing criteria and what it seeks to do. Again, we're managing both the small and large storm events. For the larger events, we're having release rates that are more similar to the natural conditions. The goals that are seeking to achieve is if we're using things like extended detention and we're pairing that with other practices for water quality, we're capturing sediments, reducing pollutants, and then also protecting diverse habitat. We're also protecting against channel erosion, like I mentioned. And even though they're uncommon, those large events can and do happen. I mean, we saw the example just last year. So those controls are needed to reduce the potential for flooding and downstream property damage. And with that, that is the quick recap of what is in the unified sizing criteria. As I mentioned, I think Aaron emailed out to most people that were on the mailing list the unified sizing criteria chapter, which goes into a lot more detail that's intended for engineers to use so they understand what's really the mathematical calculations on how you measure all these things. So if you weren't on that mailing list or didn't receive it, make sure to let Aaron know so you can get a copy of that. It's still in its draft form, but it's really, really close to being done. So we would expect with a few kind of last round of comments from the committee, the technical committee, we'd take it to the large committee for approval, and then